we'll go ahead and start off with DR. I want to make sure we get through that today. Okay. So remember, DR, direct capture digital, or just direct radiography, uses a device that is connected directly to the computer, wirelessly or wired, and there's no physical large processor that an imaging plate is brought into like with CR. So we have to do a couple important things in order for DR to work right. In DR, basically what you have is, let me zoom in on this for just a moment. Basically what you have is, you have a plate, and that plate consists of a matrix, a grid of tiny little squares that detect radiation, okay? So that's the representation of the matrix, or the active matrix array. And so in order for DR to be cost effective and worthwhile, we had to be able to develop inexpensive detector elements, because you can have expensive detector elements, each little DEC cell, and then the machine's expensive, okay? But so they had to be inexpensive, okay, in order for everyone to be able to afford it. These little cells here are the equivalent of pixels on a TV screen. So if the pixels on a TV screen output light, these detector cells catch light. They catch X-ray, okay? Each one catches X-rays, and each one is like a pixel on a screen, okay? So we call them DEC cells, detector elements. So we had to have them, we had to make them first. Someone, engineers, fancy pants, smart people had to make them, okay? And they had to be inexpensive, okay? And that way everyone can afford it. The second requirement is they had to be small, okay? We had to be able to make them small enough to where we couldn't see them. You know, we have good high resolution monitors, right? But your high resolution monitor would mean nothing if your detector cell was 10 times the size of a pixel, right? Then you're still going to end up with grainy, blocky images, okay? So you had to have small detector cells, detector elements. So miniaturization of the DEC cells and inexpensive ones. This has been around for a minute. We've had DR since the 80s. Okay, we just hasn't become affordable until last 10 or 20 years ish. But yeah, so the first clinically useful DR system developed in the 1980s was called scanned projection radiography, which was a type of CT, which is like CT is a computed tomography. A tomogram is a cross-sectional slice of the body. Computed tomography is that done on computer. And it needed things. It needed special equipment, such as something called a photomultiplier tube attached to every detector. And because it needed an extra piece of equipment to make the thing work, the detectors were very big, which explains why they were these fixed units that had to be fixed in place and couldn't be moved around. They were just large. Okay, so yeah, since then, we've been able to, we meaning, engineers and medical professionals and people who build this stuff, have been able to produce inexpensive and very small detector elements so that we can build these imaging plates that are DR, and we can't see the evidence. We can't see that we cannot see the DEC cells. That's important. So the modern DEC cell in each of these DEC cells that make up the whole cassette grid are tiny, 1/10 of a millimeter, 100 microns across. If you want something on your body that you can compare this to, your pinky nail is a centimeter across, a centimeter wide, so it's 10 millimeters wide, okay? So it's 1/100th of the width of your pinky nail. That's about the size of a detector. They're very small, okay? You can't see them on the images because they're this small. Think about it like this, though. You can only see an object on a radiograph if the object is as large or larger than a single DEC cell, right? If an object is smaller than a single DEC cell, you can't see it, okay? That gives you a physical limit to the detail you can achieve. The DEC cell is the thing that physically limits what you can see, Okay, ignore focal spot and the source to image distance and all that stuff for right now from principles of exposure. The DEC cell is what actually limits what you can see. Okay, you should contrast that against film and CR. Film and CR do not use DEC cells. Okay, they use individual molecules to detect exposure, and molecules, if you don't know, are very small, right? So with CR and film, there was almost no limit to the amount of detail you can see. You can see in principle, I know you can't see a molecule, but in principle, you could see something that's molecules in size, okay? On CR and film, that was your limit. With DR, you can never achieve as much detail. So DR, by construction, will never be able to achieve the amount of detail that film and CR can, okay? But it has a million other advantages that CR and film don't. So that's why it's better. Plus, these DEC cells are so small we can't see them with our eye anyways, right? So our eye is sort of a limiting factor. And as long as our eye can't detect the size of them, it doesn't matter how small they are, right? We don't need to see anything smaller than what our eye can see, right? So CR and film, in principle, can have much better detail than DR ever can, but the DEC cells in DR are just too small for us to see, so it don't matter. It doesn't matter at that point. Okay, good. Anyways, the modern detector cells are arranged in an active matrix array. The active part of it just means that they are turned on, right? They're waiting for, expecting exposure. And they're a flat, thin layer of these elements containing different parts. I'm going to go over these parts. They mentioned something called a thin film transistor. I'll talk about the three parts of a DEC cell in a second here. But these thin active matrix arrays give us now what we call flat panel technology. When you get into my x-ray room for lab, you'll see our DR detector. If you've worked with one, you've seen them. They're no bigger than an old CR imaging plate. They're flat, they're small. Okay, we're able to make them small because we were able to miniaturize these detector cells. Okay, so let's compare pixels to DEXels. So if you remember, a pixel is a part of your screen, right? The pixels are part of the hardware for your TV screens. This is how your images are displayed, right? You can't see it, but the screen that you're looking at, your computers, your phones, this TV, my computer, are a matrix of tiny squares, right? And each square can produce a range of colors, right? We learned about the range of colors that can be produced is dependent on the software's bit depth. If you guys remember that phrase, bit depth, dynamic range, grayscale, right? So the number of colors or shades of gray that each pixel can show is dependent on some software stuff. But importantly, pixel refers to the visual image or picture, the thing you're seeing on the screen. And is not an appropriate word for the detector elements. The detector elements we call DEC cells, detector element. So each one of these on the detector will kind of be like a pixel on a TV screen. Where the pixel on the TV screen puts out a color, puts out a shade of gray or a color, the DEC cell will be there to detect radiation. So remember, the DEC cells are embedded in the plate, right? And they sit under the patient, and each DEC cell can detect some radiation. And then just remember, voxel is, you're looking at this image, this little, square, this little image here, and you see a tree and maybe a house and some birds. But remember, that house is a three-dimensional house, right? It's not a flat house, okay? So you see pay attention to just one square, right? That house has some depth in that square. That's what we mean by voxel. A voxel is the amount of the tissue in the body or the structure of that house in the image. It has 3 dimensions to it, okay? On an x-ray, the voxel is the 3-dimensional column of tissue that's represented as just a square patch on the screen. So let's say it in another way. A DEC cell is a hardware device built into the plate, used for detecting radiation. A voxel stands for volume element, and that corresponds to a column of tissue in the patient. Detector elements, DEC cells, set up here. Pixels, picture element in the final image. You can think about them like this. There's your column of tissue or your voxel. Your voxel exposes the amount of the radiation passing through one Vox cell of the patient exposes, let's say make it easy, let's say it exposes one DEC cell on the receptor, okay? And that one DEC cell on the receptor will correspond to 1 pixel on the screen, roughly speaking, yeah.
Can you kind of describe voxels?
Yeah.
Just like, so I get a better understanding.
Yeah. So you can imagine, right, this square there being what you see on the TV screen, right? So I show you sure. Ignore digital for right now. I show you this radiograph, right? Get it there. Whatever, stay there. So I showed you this radiograph, right? Didn't matter what radiograph it was. And how many dimensions? What is this a 2 or 3 dimensional thing we're looking at? Like the actual image we're seeing. It's a 2-dimensional image, right? It's flat, right? It has a width and a height, right? And so if I took and I drew a square on here, like that, right? Not a good square, but it's a square. Okay, so I drew that square. I see some tissue inside of that square, right? That tissue has a depth to it. So you can imagine this square extending through the body this way and representing a square column of tissue. That tissue column is the voxel. Okay? So one column of tissue exposes the radiation passes through that column of tissue, right? And exposes 1 DEC cell, and 1 DEC cell will be represented as 1 pixel on the computer screen. That's the idea. Okay, good. It's a good question. So that's a voxel. Don't worry too much about the voxel. Just remember that, the body is going to correspond to, you see an image displayed on the computer screen. That image corresponds to 1 column of tissue in the patient. Okay, and the radiation had to pass through that column of tissue in the patient to expose the DEC cell. Okay, I'm going to move forward. I know. So for whatever reason, people like to name things in goofy ways, and so we had voxel, dexel, and pixel, all very similar to each other. So try to work on remembering the difference. All right, so we're going to get a little bit technical now. We need to zoom in now and look at a single dexel to see what's going on inside of it, okay? So here we've zoomed in on 1 single dexel. Remember, this square dexel that we're looking at is 1/10 of a millimeter across. They're teeny tiny. So picture your pinky split up into 100 dexels wide and 100 dexels tall, right? Your pinky nail is roughly a square, right? So 100 dexels wide and 100 tall. You can fit 100 times 100 dexels inside your pinky finger nail. Okay, so they're tiny, right? But we've zoomed in and zoomed in on them now. And so let's take a look at what they're made of, okay? So first off, you have something called the detector surface. That's important, right? The surface, the area, the thing that detects radiation. What can X-rays do? They can pass through things, right? Think about what X-rays do to individual atoms, though. They can ionize the atoms, right? I have new people in the class who have you guys heard the word ionize before? Sounds familiar. Maybe wouldn't be able to tell me what it meant, though, right? That's good, because you shouldn't be able to. X-ray tech should, though, once you learn this stuff. So what in the world is the word ionizing, and what does it have to do with X-rays? So what's ionizing?
Photon comes in, and then it crashes into the one, and then it's coming with a lot of force, so it ionizes it.
So you have a happy atom, right? And a happy atom has what?
Stable.
A stable happy atom has electrons orbiting around it, right? Hopefully you've seen the picture of an atom, right? You picture an atom in your head, okay? Yeah, there's one over there. Good. So you picture an atom, right? An atom has a dense nucleus, protons, neutrons. Ignore the neutrons for right now, but protons in the nucleus. And it has orbiting around it, we call them electrons. So we have protons and electrons, okay? And there's going to be an equal number of those two things, okay? A nice, happy, neutral atom has an equal number of those two things, okay? So if you're oxygen, you have 8 protons and 8 electrons, okay? And by the way, most of your body is oxygen, okay? You're mostly water, and water, the biggest part of water is oxygen, so you have more oxygen in your body than anything else, okay? So you have a happy oxygen atom with 8 protons, 8 electrons, and an X-ray photon comes flying in at the speed of light and happens to strike that atom, okay? What it can do is it can break that atom apart, okay? It can take and strike an electron, and it can shoot one of the electrons orbiting around it away from the atom, okay? You had a happy atom that had the same number of protons and electrons, and now you've removed one of them, okay? X-rays can ionize something. Ionizing, the definition of ionizing is to create a charged particle. Well, what I didn't say was electrons have a negative electric charge and protons have a positive electric charge. And you had a neutral atom with no electric charge and an equal number of both, right? 8 positive, 8 negative equals 0 electric charge. Right? If you take plus 8 and you say add minus 8 to it, you get the answer of 0, right? So 0 electric charge. You split it apart, and now you've got 2 electrically charged things, okay? And those things can zoom around the body and cause harm, okay? That's ionizing. Good. Fast forward now to a semiconductor, okay? X-rays can take atoms and can ionize atoms. It can make electrons jump off of atoms. That's important, okay? And so what do we call things that allow electricity to flow easily? A conductor. What do we allow things that do not allow electricity to flow?
Insulators.
Insulators, right? So what's an example of a conductor?
Water.
Water's a great conductor, right? That's why you can get electrocuted if you stick a fork in an electrical socket, right? But that fork is metal, and that fork will conduct electricity to you no problem, right? So metals can conduct electricity. Gold, copper, these are fantastic conductors of electricity, right? That's why we don't, that's why electricians don't make their, one of many reasons why they don't make the soles of their shoes out of gold, right? Because it conducts electricity very well, and electricians want to be insulated from the ground, so they wear big rubber boots, right? If you see any electrician, ask them about their boots. They're going to tell you their boots cost $500 or $600, and they're special boots that don't conduct electricity. They're better than your shoes are, right? The soles of their shoes, right? Insulators do not allow electricity to flow easily, okay? Now, in the middle of the road between those two things are what are called a semiconductor, okay? Semiconductors are materials that allow electricity to flow, but only under very special circumstances. For example, they will allow electricity to flow only when X-rays strike them, okay? So these detector surfaces made of a semiconductor, if visible light hits them, no electric current is created, okay? But if an X-ray photon strikes this detector surface, it generates a tiny amount of electric current. And the more X-ray that strikes that detector surface, the more electric current that's generated, okay? So a semiconductor, again, is a material that can conduct electricity under special circumstances, okay? We think of things like some semiconductors conduct electricity only at very specific voltages, okay? Others conduct electricity only when you shine a very special kind of light on them. There's a bunch of different types of semiconductors. You know one of them for sure, and that's silicon, right? Because you've probably heard of Silicon Valley, right? The place down south where they have all the computers advancements being made, Silicon Valley, right? Good. So silicon's a semiconductor, okay? Selenium is a semiconductor, okay? So we're going to learn about semiconductors here in a little bit. And the first thing to know is each DEC cell has a detector surface that needs to be able to, when X-rays strike it, it needs to be able to generate an amount of electric current, okay? And that's what's going to happen here. An amount of electric current is created when an amount of X-rays strike the detector surface. And we'll use that electric current to tell how much exposure the DEC cell received. The more exposure from X-rays, the more electric current generated, and the computer can interpret that, okay? Good. You have a detector surface. I want you to notice that, does the detector surface occupy the entire face of the DEC cell? No, right? The detector surface occupies some of the space on the face of the detector, okay? So the entire square, which would be the DEC cell, is not all detector surface. And that's going to become important in just a second. Secondly, the other two parts, a microscopic capacitor, I'll explain what a capacitor is in a second, and then a thin film transistor, TFT and capacitor. So think about it like this. The detector surface gets struck by an X-ray beam, the X-ray beam that's come out of the patient. The detector surface generates a small amount of electric current based on the amount of X-rays that strike it. that electric current needs to be stored somewhere for a short period of time before it can be sent to the computer. Because if all the detector cells send their electricity to the computer at once, it'll be chaos. Computers need things to come through serialized, right? One by one signal at a time, okay? So you have to have a battery. You have to have a place to store the electric charge created at the detector surface. That place is a capacitor. Capacitors are short-term batteries. It's like a battery, but only stores electricity for short periods of time. If anyone's familiar at all with car stereos, capacitors are a big important thing in car stereos because they allow us to make and use a lot more electricity than we otherwise would be able to get from our battery, right? So we use capacitors. Anyways, it's like a short-term battery. Number 3, the thin film transistor is a switch, on or off. Okay, so here's what happens, right? X-rays hit the detector, and an amount of electric current is generated at said detector. Remember, there's many of them. At said detector, the capacitor stores the electric charge like a battery, and then when that electric charge needs to be sent to the computer, the thin film transistor switches on. But it stays switched off until the time when that charge needs to be sent to the computer. Remember, this is part of a big grid, a big matrix of these detector cells, and each cell has to send its current one at a time, okay? So top left cell, then one over, then the next one over, then the next one over. So you do the whole first row of cells, and then the second row of cells, then the third row of cells. These cells have to wait in line in order to send their signal to the computer, so the computer can know that the electricity it's receiving, which cell it came from, okay? The capacitor stores the electricity. The TFT is a switch that turns it on or off. Okay, lets the electricity go to the computer or hangs onto it until it's ready. Okay. Now, the semiconductor detector surfaces. Okay. I've been saying this whole time that the detector surface is sensitive to X-rays, and that's true and not true. Okay. Some DEC cells are made of semiconductor called selenium. Other DEC cells are made of silicon, and it's purely up to the manufacturers, okay? And so if they want, we call them direct or indirect. I'll explain that in a minute. So if we want to take the X-ray beam and convert it directly to electric current, then our semiconductor has to be made of selenium. Selenium is sensitive to X-rays. Remember, semiconductors are sensitive to very specific things, right? Selenium sensitive to X-rays. If instead, I don't know, I do know why you'd want to do this, but think about why would you want to do this, right? If instead you want to take the X-ray beam, let it convert to visible light before it gets to the DEC cell, and then let visible light expose the DEC cell. In that case, we call that indirect conversion. X-rays are not converted directly to electricity. X-rays passing through the patient, hit the receptor, get converted to visible light, then the visible light exposes the DEC cell, okay? Those are called indirect conversion DR systems, and they use silicon. You are gonna have to remember which material is sensitive to which thing. X-rays expose selenium, visible light can expose silicon. Okay, and the efficiency of any detector element is measured by physicists as something called the detective quantum efficiency, or DQE. We won't spend a ton of time on that, but you should remember that's a term referring to the efficiency of any given detector. Okay, this next note is going to be important. Remember I said the detector surface on any one DEC cell is not covering the entire DEC cell, okay? That's going to be an important issue here. So the percentage of a DEC cell's square area, you guys know how to take a square area, right? Length times width, right? So there's a square area for each DEC cell, right? 1/10 of a micron by 1/10 of a millimeter by 1/10 of a millimeter, a little tiny square. That little tiny square is not 100% filled with detector surface. Some of that square area is dedicated to the thin film transistor switch and the storage capacitor battery, okay? So what we say is the percentage of a Dexel's square area devoted to just the detector surface is called the fill factor, okay? If the fill factor was 100%, then the whole surface would be detector, but it never is going to be 100%, okay? And there's a reason for this that I'm trying to build up to. A higher fill, so the higher the fill factor is, the more of the detector element's surface dedicated to detecting, the better, right? The more you can detect, the better. So a higher fill factor would give better contrast, higher contrast resolution. So notice it's not saying higher contrast. It's saying higher contrast resolution. That's basically a way of saying the detector, when it has more detecting surface, is better at detecting and displaying contrast. It's better at showing you contrast. It has a wider range of contrasts it can show, contrast resolution, and better spatial resolution. However, you can make the detector smaller. The Dexel can be physically smaller. There's no necessary physical limit to the size of the detector, except the actual hardware components, the switch, the thin film transistor, and the battery. At this point, they cannot be miniaturized further, okay? So they're fixed in their size. They take up an amount of area that can't get smaller, okay? So these two Dexels, one's bigger, one's smaller. The smaller one might seem better, yeah, but the thin film transistor, the switch, and the battery from one to the next have not changed in size, okay? So if you wanted to make a smaller detector, what you would want is, you would want a smaller switch and a smaller battery. And we can't smallify those two things yet, okay? So we are limited in the size of our detectors. If we tried to make them smaller than they currently are being made right now, we would lose detector surface. We would lose spatial resolution, lose detail, and our images would get worse. So the size of roughly 100 microns, a tenth of a millimeter across, is about as small as they can be right now, okay? Making them smaller would just take away detector surface from us. There's our physical limitation, okay? Once smart people, because smart people are smart, once smart people figure out how, engineers are smart. Once these smart people figure out how to make the capacitor smaller and make the thin film transistor smaller, or figure out a completely different way of building these things, then we'll be able to make their detector surfaces, our detector elements smaller. But currently, that's our limitation, the two hardware components. Okay. So I've done a little bit about explaining those three components. Let's go further. I want to make sure we have just a good understanding of this, the best we can. So how do DEX cells work? Okay, so I'm going to read straight from here, and then I might try to add on if I can. So we say the heart of the DEX cell is the microscopic capacitor. Again, what's the capacitor like? A little battery, right? A short-term little battery. It has an ability to store electric charge, making direct capture imaging possible. Here's the important part of this. The amount of charge stored will eventually be represented as a pixel value. The more charge stored, the darker that pixel will be. Makes sense, right? More charge equals more exposure, right? The less charge that capacitor receives, the lighter that pixel shows. Remember, that's sort of inverse, right? Because a pixel, when it's black, is turned off, okay? So the more charge on the detector cell, the more charge that a capacitor stores on the Dexel, the less turned on that pixel on the computer screen will be, right? If the Dexel receives no charge, no exposure, the capacitor gets no electric charge, well, then the computer screen is going to have that pixel, the pixel representing that Dexel, turned on all the way. So it's an inverse thing, okay? The pixels turn on more when the exposure goes down, on the screen, and the pixels turn on less or turned off more when the DXLs receive a lot of exposure. We can invert that, by the way. We can take in, have you guys done that in the x-ray rooms? Have you inverted your x-rays, turned the black to white and white to black? You can, it's sometimes useful. So Valeria, you said yes, right? What's an example, what's a time when that was useful to invert the colors?
The doctor wanted to see a fracture.
Yeah, sometimes seeing fractures, it can be helpful, right? It's just an extra tool, right? If your eyes are having trouble seeing things one way, flip-flopping all the shades of gray is one thing to do, right? So you can definitely do that. That's why digital has these advantages. You could never invert a film x-ray, right? You can only like hot light it or magnify it with a literal magnifying glass, right? We've got a bunch of other things we can do now that are hugely useful. Okay, so then each DXL then has also a thin film transistor. The transistor can be thought of as a switching gate that will release the built-up charge when the DXLs, when it's that DXL's turn to be read out. So it's like school or getting in line at the cafeteria, you're waiting in line, right? Each DXL has a spot in line and it gets to send its charge to the computer when it has its turn, okay? Again, they can't all send at one time. And that's how the computer will do this. The computer knows which DXL is going to read out, and then when it receives an amount of charge coming through the cables to the computer, it will know that amount of charge was from one specific DXL, so it'll put that shade on somewhere on the screen in the correct pixel location. So here's how your DXLs work at the level of atoms and molecules. So this is sort of now like a top to bottom kind of thing. So we're looking at almost like a cross section. So bottom of the DXL, top of the DXL. X-rays are coming in from the top, okay? So when exposed to X-rays or visible light, remember selenium for X-rays, silicon for visible light, okay? When exposed to X-rays or visible light, the light or X-rays will ionize molecules of the semiconductor, selenium or silicon. When you ionize something, remember, you split apart the atom, right? You take, this thing needs a little bit of love, it's old and got broken, but it still kind of works. You take the atom, right? These black circles represent an electron, okay? When an X-ray photon strikes an atom, it will, if it has enough energy, remove one of these electrons, okay? If it's an oxygen atom with 8 protons, 8 electrons, and an X-ray photon hits one of the electrons, electron goes flying off into space, right? So you have a -1 charge, a negative charge over here, and the atom left behind, what will be the net charge? Will the atom have left behind of a positive or negative charge? Positive, right? Because I've taken away one of the negative charges, right? This atom will have a net positive charge. So you have a positively charged atom and a negatively charged electron that was ejected. What do we know about opposite charges and like charges, how they're attracted or repelled from each other? What's the rule? Opposites attract, right? Positive and negative charges attract each other, okay? And like charges repel each other, okay? So an X-ray photon comes in now, follow the laser pointer around here, and splits up an atom, okay? An atom in the semiconductor. Now, what you have to do to make this work is you have to have one side of the detector element, like the surface of the detector element, already having an electric charge applied to it, okay? So a tiny amount of electric current runs through one side of the detector, okay? And when you ionize an atom in the detector material, the negative charges, the electrons that were ionized, get pulled upward, and the positive charges get pulled downward, okay? They get separated. They get pulled towards, in this case, the electrons get pulled towards a positive charge up top, and the protons, the atoms left behind, get pulled towards a negative charge down below. Opposites attract, okay? This is going to generate a small amount of electric current. And we've created an electron-hole pair. We've split apart an atom, basically. So the top electrode up here, the surface, will attract the free electrons. These negatively charged particles go upward. The DXL electrode, which is at the bottom of the DXL, has a negative charge applied to it, because we can do that. And that will pull the atoms of the silicon or selenium downward toward it. This separation of charges generates its own small amount of electric current. This is where we get the electric current from. The more X-ray photons that strike the material, the more atoms of the material are ionized and the more charge that's created, okay? The amount of charge created represents an amount of exposure that the deck cell receives. And again, more exposure, more charge. So now, each active matrix, each deck cell in this active matrix array will have received an amount of electric charge, or received an amount of X-ray exposure, will have built up an amount of charge, and then each deck cell will need to read out one by one. The array of deck cells is crisscrossed with wires called gate lines and data lines. Gate lines controlled by the address driver, which controls the order in which the deck cells read out. So again, smart people put this stuff together. These deck cells read out in a specific order, and that order is always going to be the same, okay? Each gate opens, each thin film transistor will open one at a time. So you get this one, then that one, and then the next row down, left, middle, right, next row down, left, middle, right, and it does this throughout the whole thing, okay? Remember, it's not 9 deck cells, right? It's millions of them, okay? Because just in your pinky finger, right, you've got, what, 10,000 deck cells worth, right? So it's a lot of deck cells, okay? So they're going to have to read out one at a time, and that's the deal, okay? Now, these deck cells read out an amount of electric current. They output an amount of electric current toward the computer, and the computer will run that electric current through an amplifier. The amplifier, because these are teeny tiny, right? The amplifier just does exactly that. It takes the electric current and bumps it up to a bigger amount of current. So it's just a proportional increase in electric current. That's what amplifiers do. The amplifier then runs that current through something called an analog to digital converter. I won't spend much time on that, but we call the electric current coming from the deck cells analog. That current has to be then digitized. It has to be put into a specific value. It has to be given a specific numerical value. And that numerical value is called a digital value, okay? And that value will represent a pixel value on the computer screen. And that is just it. One at a time, the deck cells read out to the computer. The computer will put, this top left deck cell will be the top left pixel on the computer screen. And this top middle deck cell will be the top middle pixel on the computer screen, and so on, right? It's not an exact one-to-one relationship, but when I explain it, it's easiest to do it like that, right? The deck cells and pixels don't have a one-to-one size relationship. The pixels might be bigger than the deck cells are, right? So it might take 10 deck cells to equal 1 pixel, but you get the idea, right? Where this deck cell is where the pixels will be on the computer screen. It will represent those pixels on the computer screen. Okay, questions here? I know there's a lot going on, but do we have questions on the basics of this process? Okay, so you have a deck cell. There's many of them on a detector plate. Each deck cell receives exposure, either from X-rays or visible light. The light or X-rays causes an amount of electric current to be created in the detector element. That amount of electricity gets stored in the capacitor, and then the computer, one at a time, reads out the amount of stored electricity and gives that stored electricity a value, a pixel value, which will be displayed on the computer screen. Okay, so that we need to now talk about, so that was basically the gist of how direct conversion works, right? X-rays would convert directly to electric current. That requires a material called selenium. However, you might want to maybe, do things cheaper, because there's cost effectiveness is one consideration when offices are deciding these things. So another way to do this, which is again more cost effective, is called indirect conversion. And as it might imply, it requires maybe one extra step. It's indirect. Direct means one thing goes to the next, right? Indirect means you got to take maybe 1 or 2 more extra steps. Okay. So what I just explained was DR, direct radiography, or direct DR. I know there's a lot of terms going around right now, but direct DR means X-rays converted directly to electricity. Indirect DR, you have X-rays get converted to visible light converts to electric current. It's one extra step. So here we go, indirect. Developed before direct systems were invented and uses silicon. Silicon was one of the first, that's why they named it Silicon Valley, not Selenium Valley, right? Silicon is one of those first semiconductors that were widely used. So rather than selenium, silicon. Amorphous just means non-crystalline, like powder, okay? So amorphous is nothing special. Amorphous means like without form, right? So amorphous, just think, there it is, even says right there. I've done this for so long, I know what to say, and then it comes up 10 seconds later in the slide. Amorphous means non-crystalline, powder form, there you go. So there it is, that's all amorphous means. So silicon versus selenium. So silicon, just because we're told so, we know, is not sensitive to X-rays, okay? Silicon is sensitive to visible light. So if you take a silicon detector and shoot X-rays at it, it doesn't generate any electric current. But if you expose it to visible light, then it generates some electric current. Okay, so the DEC cells must absorb visible light rather than X-ray photons, so we have to convert X-ray photons to visible light. That's actually, by the way, not a lot different from your old CR and film cassettes, okay? I don't think I have a good film cassette in here, but film cassettes, I don't know if you know this, but CR and film don't convert X-rays to the stored image. CR and film convert X-rays to visible light, and the visible light is what actually exposes the photographic film. In a film cassette, the film is literally photographic film. It's sensitive to visible light, not X-rays. If we didn't do that conversion from X-rays to visible light with film and CR, it would take a magnitude more exposure to actually make an image. It would take much longer to expose the images, and you need to use much more radiation. The conversion is important with CR and film, so it was always like that. Okay, DR, direct conversion DR is kind of a special thing. Okay, indirect conversion DR is closer to how film and CR radiography work. So the entire active matrix array is overlaid. Laid on top of it is something called a scintillation screen. A scintillator is a material that converts one kind of light into another. So if you don't know that, a scintillator is a material that converts one type of light to another. You need to know the possible different scintillator materials that can be used. So they are cesium iodide, that's what ours is here, by the way, or gadolinium oxysulfide. You do not need to know, so my computer just started to get wacky just now.